How you doing, guys? Welcome to another video. This is 18.2, calculations involving acids and bases. Higher levels, let's go. Okay, volume 7, we basically look at some calculations in this video. We look at H plus calcs, OH minus calcs, and then we need to do some pH and pOH. And we also talk about working out the H plus and OH minus concentration at some different temps. Applications and skills basically focus around solving the problems, and there's a few guidance points that I'll touch on in this video as well. So we've seen this in standard level that the concentration of H3O plus multiplied by the concentration of OH minus is always equal to 10 to the minus 14 at 25 degrees, and that comes from the ionic product of water. Now this is an equilibrium relationship, so that means it has a K value. In this case, the K value is 10 to the minus 14, which we've described as being the KW value. Now, what happens if we change the temperature? Well, in all equilibrium systems, if we change the temperature, we change the K value. And it's known that the self-ionization of water is endothermic. And I would strongly encourage you to remember that. You don't have to remember the value, but remember that that process is endothermic. That's where two water molecules could react to form H3O plus and OH minus. So that means that energy would be on the reactant side. So what would be the impact of the pH of pure water if the temperature was increased? Okay, well, if we increase the temperature, the system would like to adjust to reduce the temperature. So that means the equilibrium expression is going to shift to the right. What does that mean for the concentration of H3O plus? Well, it means it's going to increase. So our hydrogen ion concentration will go up. That means that the pH will then start to go down because it's becoming more acidic. But please remember, this is pure water, so it's still a neutral solution. Just because the H plus goes up, the OH goes up as well because they're on the same side. So it's still a neutral solution, it just has a lower pH. Well, what happens if the temperature is decreased? Well, if the temperature decreases, the reaction is going to shift to the left. That means our H3O plus concentration is going to go down and our pH will ultimately go up. Now the same process will happen before because OH minus and H3O plus are on the same side, then that means the system will still be neutral. There'll still be the same amount of H3O plus as there is OH minus, just the pH will be slightly greater. Some of the key acid bases formulas are on the screen right now, and these are simply ones that you need to remember. They're not found in the data book, so the more you can use them, the more skills you have, the better that you'll be. So we have the pH and H plus calculations, and then on the right we have the pOH and the OH minus calculations, and in the middle we have pH plus pOH equals 14. So calculate the H plus and OH minus concentration of a solution of 65 ml of 0.105 molar KOH at 25 degrees. So start by writing an equation. KOH dissociates into K plus and OH minus. It dissociates because it is an ionic compound. It's an alkaline substance. It dissociates. So that means we have 0.105 molar KOH. The 1-to-1 ratio suggests that we would also have 0.105 molar OH minus. So we've worked out our OH minus. Now we can work out our H3O plus or our H plus by using the ionic product of water. KW, which is 10 to the minus 14, divided by the concentration of OH minus, which is 0.150, will allow us to calculate the concentration of H3O plus. If you're struggling understanding that step, I suggest you go back and watch the video on this section of the course in the standard level section. That gives us a concentration of H3O plus at 9.52 times 10 to the minus 14. Then we might be asked to calculate the pH and the pOH of the solution. Well, the pH is equal, or the pOH is equal to the negative log of OH minus. The little p before the OH means just take the negative log of the value. So the negative log of 0.150 will give us our pOH. That equals 0.979 Our pH we could then calculate in a number of ways, but I'm going to use the formula 14 take away pOH to work out the pH. It just seemed simpler, it was an easier calculation to do. Keeping the numbers in your calculator before, we see that the pH is equal to 13. Now I know that looks a little bit funny, but I have rounded those numbers a little bit. Keep the numbers in your calculator, round right at the very end. Okay, another example. The pH of a sample of coffee is 3.47 at 298 K. Calculate its pOH, H plus, OH minus, and deduce if the solution is acidic, basic, or neutral. Okay, so another example. The pH of a sample of coffee is 3.47 at 298 K. Calculate its pOH, H plus, OH minus, and then deduce if the sample is acidic, basic, or neutral. Well, we've been given the pH in the question. The pH equals 3.47. So the simplest thing to do now is to calculate the pOH by doing 14 take away the pH. They told us it was at 298 K, so that means we've got standard conditions. So our pOH is equal to 10.53. From those two values, I can work out the H plus concentration by doing 10 to the negative pH and the OH minus concentration by doing 10 to the negative OH. So working those two values out, I've got the H plus equal to 3.39 times 10 to the minus 4 molar. And then I can do the same for the OH minus, which is 10 to the power of negative 10.53. And this is going to give me a very small value because this sample of coffee is in fact acidic. The concentration of H plus is greater than the concentration of OH minus, which means it's an acidic solution. Concentration of OH minus was worked out to be 2.95 to 10 to the negative 11, which is a very small amount of alkali solution. Because the H plus is greater than the concentration of OH minus, it would be referred to as an acidic solution. Okay, another example. 340 centimeters cubed of a solution of sodium hydroxide is mixed with 265 centimeters cubed of a solution of potassium hydroxide. Calculate the pH of the resultant solution. I would refer to this as an addition of solutions question. We've got one solution and another solution. They both contain hydroxide ions, and then we've tipped those two solutions together. Because they are in fact just bases, there will be no reaction. If it was a reaction, we would need to take a very different pathway. But because it's just an addition of solutions, we can do this question quite simply. The first step is to calculate the number of moles of hydroxide ions in both of the solutions. So in the first solution, the number of moles of hydroxide ions is 1.14 times 10 to the minus 3 mole. In the second solution, we do the same thing, work out the concentration times the volume to work out the number of moles of the hydroxide. So 8.45 times 10 to the minus 4 times 0.265, converting to decimeters cubed, don't forget that step, gives us our number of moles of hydroxide, and now we have the number of moles in both of the solutions. So now what we need to do is work out the number of moles of alkali in total, so we simply add those two numbers together. We've tipped the two solutions together, so we've added the number of moles, so I've just added those two numbers together. The concentration of OH minus can now be determined by doing the number of moles divided by the volume in total. Now our volume in total was 340 plus 265, and then we need to convert that to decimeters cubed to work out the concentration. So the concentration of OH minus was 0.00191 molar. And now the simplest way to work out the pH will be to go down the pOH path. So determine the pOH, and then I can work out my pH by doing 14 take away 2.72. I've assumed this is at 298 K because they haven't told me otherwise. Okay, volume 7, some top tips. Make sure you write the equation for either dissociation or ionization, and make sure that you use the ratio correctly and the equations and the formulas. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe for more, and I'll see you next time.